Welcome to a lesson with Dr. Powell. Let's take a look at a way of picturing a left inverse. Okay, so we have a linear transformation that comes from a domain and it's injective. So maybe it goes into a space like R3. Imagine this is like R2 over here. So um, somewhere R2 and the codomain is R3, but the range doesn't hit all of R3. It's not surjective necessarily, but where it won't be in this particular instance. But suppose that it's injective, meaning that the range is an isomorphic copy of the domain, all right, as it hits. So what's a left inverse here as we're going back? That's simply a linear transformation that goes back from the codomain to the domain, such that when you restrict that, or you only look at what its action is just on that isomorphic copy of the domain that F sends us to, and you just go back, it's going to be an isomorphism between the domain and that isomorphic copy of the domain, the range. So the range and the domain, there is an isomorphism between them, and G and F work together to give us that with proper restrictions if we restrict ourselves into the right places. So that's kind of what it is. Now, if I take a point outside of the range, like out here, it's still in the domain of G, and G will still run it back to the domain. But there are different types of left inverses that we can have. All right. So that's what a left inverse is. Okay, and there's different types of left inverses. So here's an example of that. Suppose, for instance, that this function from here to here is given by something like this in the column interpretation. Maybe it's 1, 0, 1, negative 2, 1, 0. So it goes R2 to R3, and it outputs this plane in here. Now here's an example of two different left inverses. 0, 0, 1, 0, 1, 0. This is one potential one. And we also have 1, 2, 0, and 0, 1, 0. Both of these are acceptable left inverses. They both behave the exact same way on the range. So given any 2 points here, both of these will act the same and give you the same elements back in the domain back this way. So really these two guys function the exact same way when we're on the range. So even though they're different functions, they stay the same here, but they'll change up when we throw in points that are outside of the range as we go back. So one way of actually knowing if we are in the range or not of a function is if we have a left inverse for it, then what we can do is we can take that codomain element, throw it into the left inverse, see where it goes in the domain, then follow F back. And if we get to the exact same point that we started with, we're in the range. Now, if we get to a different point, that's because we were outside of the range, because we can't get back out here if we running back this way to the domain and then isomorphism back to the range here. So this is a for sure way to tell whether we're in the range or not. So if we have a system of equations, and maybe our map F represents that, and the codomain of the map actually can represent like what happens after the equal signs. So you can kind of think, okay, is the thing that happened after the equal sign actually have a solution? That's the same way as saying it's in the range of this function f, and we can tell by running it through the left inverse and then going back, and we can tell if it is. Now, this actually is quite common in various applications. One in particular is with transmitting signals or signal processing. Sometimes we buffer code or buffer our messages, our signals a little bit, and we can run. And by running a left inverse through, we can actually see if of our buffering function, we actually can can see if things have changed as the signal has gone through the channel or not. And that's like saying it's like in the range of something. So this really does have some applications and some uses in more than one place. But nonetheless, this is a way of picturing what's going on with it. Thanks for watching.